This is a video from section 4.4. The directions say find the limit. Use L'Hopital's rule where appropriate. If there is a more elementary method, consider using it. All right, so we're going to take a look at example 1. And example 1 says to find the limit as x goes to 3 of x minus 3 divided by x squared minus 9. Now, we could use the methods of chapter 2 to evaluate this limit. So what we're going to do is take the limit as x goes to 3. Now, the denominator is a difference of squares, so we can factor it as x plus 3 times x minus 3. The numerator can be factored as 1 times x minus 3. And the reason why I do that is so I can force you to see x minus 3 is in the numerator as a factor. And then what I'm going to do is I'm going to cancel the x minus 3's. And then I'm going to write this as the limit as x goes to 3 of 1 over x plus 3. And so this is 1 over 3 plus 3. And so the answer to the first example is 1/6. Example 2. Now, in example 2, we have the limit as x goes to negative 2 of x cubed plus 8 divided by x plus 2. So let's write that a little bit closer. Now, before we do this, recall that a cubed plus b cubed is a plus b times a squared minus ab plus b squared. So that's how we factor a sum of cubes. And so this is the limit as x goes to negative 2. We can leave the denominator alone, but again, I'm going to still write it as 1 times x plus 2, so you see the x plus 2 as a factor. And then the numerator is x plus 2. Now I'm going to square the first term, which is x squared, multiply these two terms together, right, the x and the 2, and change the sign. And then I'm going to square the last term. But the x plus 2's cancel, and this is the limit as x goes to negative 2 of x squared minus 2x, and then 2 squared ends up being 4. So I'm going to pop a negative 2 in for x, so I'm going to get negative 2 squared minus 2 times negative 2 plus 4. So this is 4 plus 4 plus 4. And so the answer to example 2 is 12. Example 3. And so far, as you can see, we haven't needed to use L'Hopital's rule. And I do think it's beneficial to do these limits this way so we don't forget how they work in chapter 2. So suppose I have the limit as x goes to 4 of the square root of x minus 2 divided by x minus 4. Now, remember that a squared minus b squared is a plus b times a minus b. And so I could view the denominator as a difference of squares. So there is another way to do this by multiplying the numerator and denominator by the conjugate of the numerator. So that is an alternative, by the way. So I'm going to take the limit as x goes to 4 of the square root of x minus 2 divided by, Now, I'm going to write the denominator as a difference of squares. So I'm going to write this as the square root of x squared minus 2 squared. So we can view it as a difference of squares. And so this is the limit as x goes to 4 of 1 times square root of x minus 2 divided by square root of x plus 2 times square root of x minus 2. But if you notice, the square root of x minus 2's cancel, and this is the limit as x goes to 4 of 1 over the square root of x plus 2. And so I'm going to replace x with 4. And so the answer here is 1 over 4. That's example 3. Example 4. So we're going to do one more example where we really don't need L'Hopital's rule just yet, but we will start to need it on example 5. So we're going to take the limit as x goes to 0 of tangent 3x divided by sine 2x. Okay, now I want you to recall a couple of things. This is back in chapter 3. The limit as x goes to 0 of tangent x over x is 1. So we can show that. And then the limit as x goes to 0 of x over the sine of x is also 1. So we need these two ideas to do this problem. So what I'm going to do is I'm going to write the limit this way. So I'm going to write this as tangent of 3x divided by 1 times 1 divided by sine 2x. Okay? Now, if I want to take advantage of these two results, well, I'm going to need something. Now, if you notice the numerator has an x in it, if you notice there's a tangent of 3x. The denominator is missing an x. So what I'm going to do is I'm going to put it in. But if you notice over here, notice how the numerator is missing an x because I want to take advantage of the second result. And so I'm going to put an x in the numerator. And that's legal because what I did was basically multiply by 1. And then what I'm going to do is I'm going to split off that limit. So I'm going to take the limit as x goes to 0 of tangent of 3x over x times the limit as x goes to 0 of x over sine 2x. Now, I want the argument of the sine and the numerator to match up. And the only way that's going to happen is if I multiply the numerator in that second limit by a 2. But if I multiply the numerator by a 2, I have to divide by 2 on the outside of the limit so I don't change its value. Because remember, half of 2 is 1, and anytime you multiply by 1, the number doesn't change, right? So remember, again, the argument of the sine and the numerator have to match for this limit to be 1. So we have to make them match. And just like for the tangent, the argument of the tangent and the denominator have to match. To get them to match, I'm going to multiply the denominator by 3. But if you multiply the denominator by 3, I have to multiply the limit by 3. Because 3 over 3 is 1. And when you multiply by 1, the value doesn't change. Now we're free and clear. So this is going to be equal to 3. This limit, this first limit is 1. And I'm going to go multiply by half. And the value of the second limit is also 1. And so the answer to example 4 is 3/2. So the key to this type of problem is to make sure that the numerator and denominator have that x you need. And so we had to put it in this second line for this example to make sense. Okay? That's how you do example 4. Let's take a look at example 5. So if you notice in the first 4 examples, we did not need L'Hopital's rule at all. Well, now we're in a situation where we're going to need L'Hopital's rule. So we're going to take a look at the limit as x goes to 0 of 8 to the x minus 5 to the x divided by x. Now, if we look at the limit as x goes to 0 of the numerator, that's 0. And the limit as x goes to 0 of x is equal to 0. So, therefore, I'm going to say the limit is an indeterminate form of type 0 over 0. So we're going to apply L'Hopital's rule. So we'll do that on the next page. And so I'm going to take the limit as x goes to 0 of 8 to the x minus 5 to the x divided by x. And so that's going to be the limit as x goes to 0 of. Now, we're going to take the derivative with respect to x of 8 to the x minus 5 to the x, and we're going to divide by the derivative with respect to x of x. And so that's the limit as x goes to 0. Now, the derivative of x is 1. The derivative of 8 to the x is 8 to the x times natural log of 8. So we've done those, okay? So remember, if y equals a to the x, y prime is a to the x natural log of a. Now remember, a is greater than 0, and a can't be 1. And then the derivative of 5 to the x is 5 to the x natural log of 5. Now I can stuff that 0 in. And so this is 8 to the 0, natural log of 8, minus 5 to the 0, natural log of 5. So this is ln of 8 minus ln of 5, which is natural log of 8 over 5. So the answer to this example is natural log of 8 over 5. And so that's how you do a problem where there's L'Hopital's involved. So let's take a look at example 6. Suppose I give you the following. Well, suppose I had the limit as x goes to 0 of arc sine x divided by x. Now, here, I'll write that over here. So the limit as x goes to 0 of arc sine x is 0. and the limit as x goes to 0 of x is also 0. So what we can say is this limit so you notice this limit has the indeterminate form of type 0 over 0, right? So let's write that down. I'm going to write it. So let's write it down. So we're going to apply L'Hopital's rule. So I'm going to take the limit as x goes to 0 of arc sine x divided by x. And so this is the limit as x goes to 0. Now I'm going to take the derivative of the arc sine x and divide by the derivative of x. And so this is the limit as x goes to 0. Now, the numerator is 1 over the square root of 1 minus x squared. That's the derivative of the arc sine. The derivative of x is 1. Well, if we evaluate that, we can say the limit as x goes to 0 of 1 over the square root of 1 minus x squared is equal to 0. Therefore, the limit as x goes to 0 of arc sine x divided by x must also, let me back up. As x goes to 0, let's plug that in. We get 1 over the square root of 1 minus 0 squared, right? That's actually 1. And so this limit as x goes to 0 of arc sine x over x must also be 1. And that's how you do, this should be example 6. So let's take a look at 2 more examples for this video where we apply L'Hopital's rule. So suppose I had suppose I had this. Suppose I had the limit as x goes to infinity of x plus x squared divided by 1 minus 2x squared. Now, I want you to notice something. When I take the limit as x goes to infinity of the numerator, I get infinity. And when I take the limit as x goes to infinity of the denominator, I get negative infinity. So the limit is an indeterminate form of type infinity over infinity, right? That's negative, that's fine, but that's the idea, okay? Now, so I'm going to take the limit as x goes to infinity of the numerator should be x plus x squared, and the denominator is 1 minus 2x squared. And so this is the limit as x goes to infinity of the derivative. So we're going to apply L'Hopital's rule. So infinity over infinity is an actual indeterminate type where we can use L'Hopital's rule. And so we're going to take the derivative of the numerator and divide by the derivative of the denominator. Now, so this is going to be the limit as x goes to infinity of 1 plus 2x divided by negative 4x. Now, what you can do, we could either do L'Hopital's rule again, which is fine, or I can show you how to evaluate that. We can't just plug in infinity, because when you do, you're going to get infinity over negative infinity, which doesn't make any sense. So I want to give you some tools when I do these types of problems, okay? I want to show you how I'm thinking about it. So what you can do is divide numerator and denominator by x. And then when you do, you get 1 over x plus 2, right? Here, in fact, let me write this. I get 1 over x plus 2x over x divided by negative 4x over x, okay? And so this is the limit as x goes to infinity of 1 over x plus 2 divided by negative 4. But if you notice, as x gets large, this term that I'm circling will go off to 0. And so this limit should be 2 over negative 4, which is negative a half. And so the answer to example 7 should be negative a half. And that's how you do example, again, that's how you do example 7. Let's go ahead and do one more problem here. We'll call this good on this last problem for this video. So if we look at example 8, so what I'm going to do is look at the limit. Yeah, we're going to do an infinity problem. So we're going to look at the limit as u goes to infinity of e to the u over 10 divided by u cubed. Now, I want you to notice the limit as u goes to infinity of e to the u over 10 is infinity, and the limit as u goes to infinity of u cubed is infinity. So this limit has an indeterminate form of type infinity over infinity. And so we're going to apply L'Hopital's rule here. So I'm going to take a look at the limit as u goes to infinity of e to the u over 10 divided by u cubed. And so this is the limit as u goes to infinity of, now we're going to take the derivative of the bottom, which is u cubed, so I'm going to write it that way. And then I'm going to take the derivative of the numerator, which is the derivative of e to the u over 10. And we're going to take the limit of that as u goes to infinity. So this is the limit as u goes to infinity of, the denominator is 3u squared. The numerator is 1/10 e to the u over 10. So this is chain rule. So let's write that on the next page. We have the limit as u goes to infinity of The denominator is 3u squared. And then we have the numerator is 1/10 e to the u over 10. Now this has the shape of infinity over infinity again. And so we're going to apply L'Hopital's rule again, right? So just like over here, we're going to take the derivative of the numerator divided by the derivative of the denominator. And so this is the limit as u goes to infinity of, now I'm going to have 1 over 100 e to the u over 10 divided by 6u. Again, we have infinity over infinity, so I could apply L'Hopital's rule again, and this is the limit as u goes to infinity. If I take the derivative of the bottom, I get 6. If I take the derivative of the top, I get 1 over 1,000 e to the u over 10. And interestingly, when you plug in infinity, you're going to get the answer of infinity. And when you get infinity, that's just a fancy way to say the limit doesn't exist. And so this is a pretty good stopping point. This will conclude this video for section 4.4. And we did 8 examples on finding the limit, where 4 of them we had to apply L'Hopital's rule. So, okay, thank you. So this will be part 1, and I will make another video, and I'll call it part 2, with some different kinds of problems. Thank you.